In this session, we will try to understand the views of few more scholars in the understanding the concept of isostasy. In the earlier session, we also tried to understand the concept of isostasy, which is the state of equilibrium or balance between various surface features like mountains, plateaus, plains and ocean basin. These features are in a natural state of hydrostatic equilibrium. The question which arises here is that whether this state of equilibrium between various surface feature is permanent. If it is not permanent, then why this state of balance is disturbed? If this balance is disturbed, how it is restored, and so on. To understand the contribution of various scholars to the concept of isostasy, to understand why isostatic disequilibrium occurs and how it is adjusted, to know whether the isostasy is local or regional in nature. The concept of 𝗧𝗧𝗧𝗧𝗧𝗧𝗧. 𝗧𝗧𝗧𝗧𝗧𝗧 presented a new concept of isostasy in 1933, in which he combined the concept of both 𝗧𝗍 and Pratt's. According to him, density of rocks varies within the column and between the columns. For example, rocks of a column at sea level have higher density, say 2.676 grams cubic centimeter, than at higher elevation of the same columns, say 2.7 grams cubic centimeter, which means as we go downward, the rocks of a section of the earth crust become denser. Density increases downward. Similarly, density of the rocks of different sections or columns of the earth crust also varies. Thus, it appears that density of rocks varies vertically and horizontally. The views expressed by Hayford and Bowie about the isostasy were in agreement with that of Pratt. They have propounded their concept of isostasy almost similar to the concept of Pratt. According to them, there is a plane where there is complete compensation of crustal parts. Densities varies within the elevation of columns. Crustal parts above the plane of compensation, the density of mountains is less than the ocean floor. In other words, the crust is composed of lighter material under the mountains than the floor of the oceans. Below the zone of compensation, the density is uniform laterally. Thus, according to Hayford and Bowie, there is an inverse relationship between the height of the column of the crust and their respective densities above the line of compensation. The plane of compensation is supposedly located at a depth of 100 km. The column having the rocks of lesser density stand higher than the column having the rocks of higher density. Their varying densities in such a way that they exert equal downward pressure at the level of compensation and balance each other. Based on the comparative study of 𝗧𝗍 and Pratt's on isostasy, Bowie concluded that there was a great deal of similarities in their views. Bowie could observe a glimpse of the concept of root formation and the law of flotation of 𝗧𝗍. The concept of Hayford and Bowie that the crustal parts are in different form of various surface features are in the form of vertical columns is not tenable, because surface features are found in the form of horizontal layers. Joly presented his views on isostasy in the year 1925. The views advocated by Hayford-Bowie were criticized by Joly. His main objection about the existence of level of compensation at a depth of about 100 kilometers. In his opinion, temperatures would be so high that all the rocks would melt and become liquid at such depth. High temperature would cause liquefaction and thus level of compensation would not be possible. Joly further refuted the concept of 𝗕𝗏𝗺𝗵 that density varies above the level of compensation but remains uniform below the level of compensation. He refuted this concept of Bowie on the ground that such condition would not be possible in practice because such condition would easily be disturbed by the geological events, and thus the level of compensation would be disturbed layer 16 kilometers or 10 miles thickness below the shell of uniform density. The density varies in the zone of 10 miles thickness. It is thus appear that Joly assumed the level of compensation as not linear phenomena but zonal phenomena. Joly did not conceive the level of compensation as a straight line but as a zone of compensation. He did not believe in a line or level of compensation, rather believed in zone of compensation of 10-mile thickness. In Joly's concept of isostasy, we also find a glimpse of law of flotation. The view is closer to the flotation theory of Airy. The areas of low density in the 10-mile layer corresponds with the downward projection of the lighter continental crust, while those of high density represents the intervening areas filled with material of heavier substratum. In the opinion of Joly, the Earth's crust consists of lighter material, that is Cl, whose average density is 2.67. The Cl is floating over Cima like an iceberg. Thus, these views are in conformity with the model of Earth's crust, in which lighter continental masses float on a denser substratum. The views of Arthur Holmes on isostasy to a great extent were also similar to that of Airy. Holmes also assumed that the understanding of crustal parts or the higher relief features of the Earth's surface are composed of lighter material, and in order to balance them, major portions of the elevated areas or higher columns are submerged up to a greater depth. He is of the opinion that mountain ranges have roots largely composed of lighter cealic rocks, going down greater depth. According to Holmes, the higher columns are standing because of the fact that there is a lighter material below for greater depth, whereas there is lighter material below the smaller columns like plains up to less depth. In the year 1978, A. Holmes and D. L. Holmes have tried to explain the concept of isostasy with the help of a diagram which shows characteristic example of crustal columns, each of which has the same area and extend downward to the same depth below the sea level. They tried to illustrate the concept of equal weight along level of equal pressure. These columns are plateau 4 km high, plateau 1 km high, plain at sea level, ocean 5 km deep. Each column has a thickness of 50 kilometers. The figures to the right of each column denote average density, and M stands for Mohorovic discontinuity. According to them, the total weight of each column along the line of equal pressure can be obtained by summing up the product of the density and corresponding thickness. The plateau of 4 km high from the sea level, 54 into 2.8, that is average density, is equal to 151.2. For plateau of 1 km high, 36 into 2.8, that is continental crust, plus 15.33 into 3.3, that is mantle 𝗓𝗧, is equal to 150.3. For the plain near the sea level, 30 into 2.8, that is continental crust, multiplied by 20 into 3.3, that is mantle 𝗓𝗧, is equal to 150.0. For oceans of 5 km deep, 5 into 1.03, that is sea water, plus 1 into 2.4, that is sediments, plus 5 into 2.3, 9, that is crustal 𝗓 plus 39 into 3.3, that is mantle 𝗓. The total comes to 150.75. A perfect isostatic balance is possible only theoretically. There is no complete isostatic adjustment over the globe because the earth is dynamic, unstable and unresting. The exogenetic and the endogenetic geomorphic processes continuously are operating on the earth's surface and therefore disturb the isostatic equilibrium. In fact, the endogenetic forces and the resultant tectonic events cause disturbances in the ideal conditions isostasy, but the nature always tends towards the isostatic adjustment. That is, nature always tries to bring back or restore the state of isostatic equilibrium. The state of equilibrium of various surface features is also disturbed by the exogenetic processes like denudation of elevated areas like mountains and plateaus and deposition of the eroded material into the low-lying areas or plains or the ocean floor. For example, a newly formed mountain due to tectonic activities is subject to severe denudation over a period of time. Consequently, there is continuous lowering of the height of the mountains. Due to the denudation of the mountains, the mountainous areas gradually become lighter. On the other hand, the eroded material or sediments are deposited in the ocean floor. Due to the processes like denudation of the elevated areas and deposition of material in the depressed areas like ocean floor, there is a continuous increase of weight of sediments on the sea floor and therefore, that is, ocean floor becomes heavier. Thus, the isostatic balance between these two areas is disturbed, but the balance has to be restored or maintained. The superincumbent pressure and the weight over the mountain decreases because of the continuous removal of the material through denudational process. This mechanism leads to gradual rise of mountainous areas. Continuous sedimentation on the ocean floor causes gradual subsidence of the sea floor. In brief, when an uplifted landmass like mountain is worn down by agents of erosion, the load of the underlying column of the crust is reduced by the weight of the material that has been eroded away. That is, unloading of the material from mountainous areas. At the same time, deltas or the sea floor where denuded material is being deposited receives sediments leading to the loading of the sediments. The loading and unloading of the crustal material disturbs the state of isostatic balance. There must be slow flowage of relatively heavier material of substratum, that is 𝗓, from below the sea floor towards the lighter material of the rising column of the mountain below the level of compensation. Due to the loading of sediments on the ocean floor, it starts sinking due to the pressure exerted by the material. At the base of the crust, the pressure exerted by the loaded column increased. In response to this, the flow of 𝗓 from under the loaded column towards the base of the unloaded column, that is mountain. The 𝗓 from the loaded column moves towards the base of the mountains and therefore, in the process, the unloaded column rises. This mechanism leads to gradual rise in the mountains and gradual subsidence of the ocean floor. The isostatic balance is restored by the movement of 𝗓 from one column to another. This is called as isostatic adjustment. Sometimes endogenetic forces act so suddenly and violently that the state of isostatic balance is thrown out of the gear all of a sudden, and the isostatic adjustment through the process of flowage of material from the substratum is not maintained. Similarly, sometimes climatic changes occur at extensive scale, which greatly influences the isostatic balance. Today, anthropogenic activities like construction of major reservoirs or multi-purpose projects are disturbing the isostatic balance, leading to reservoir-induced seismicity. At the global level, we can see that extensive parts of North America and Eurasia subsided under the enormous weight of accumulation of thick ice sheets during the Pleistocene glaciations. But the landmass began to rise because of the release of superincumbent thick load of the ice sheets due to deglaciation and consequent melting of the ice sheets about 25,000 years ago, and thus isostatic balance was disturbed. The raised beaches of Finland, Scandinavia show that an uplift of 250 meters has already taken place during the last 8,000 years, and the region is still out of isostatic balance and rising. The land masses are still rising at a rate of 12 inches per 28 years under the process of isostatic recovery. Sometimes endogenetic forces act so suddenly and violently that the state of isostatic balance is thrown out of gear all of a sudden, and the isostatic adjustment through the process of flowage of material from substratum is not maintained. Similarly, sometimes climatic changes occur at extensive scale. As pointed earlier, there is no complete isostatic adjustment over the globe due to interplay of exogenetic and endogenetic processes operating on the Earth's crust. There is a disagreement among the scholars about local or regional nature of isostasy. Based on various studies and observations that if isostatic adjustment does not exist at the local level but exists at the extensive regional level. Hayford proved that compensation does not take place for a smaller area or at the local level. For example, Scandinavia, Greenland, Antarctica are subject to isostatic compensation. That is, compensation takes place in a large area. Therefore, isostasy is not local but regional in nature. Isostatic adjustment or compensation is very slow process. Assumed from the various theories of isostasy discussed above, several important facts and few generalizations of the concept of isostasy be drawn, which is presented here. Based on the theories discussed above, several important observations about the concept of isostasy and isostatic adjustment. 1. Gravity anomaly observation is the basis of the concept of isostasy. The 𝗂 is floating over 𝗓. The layer of 𝗂 or depth of 𝗂 is not uniform. The depth of 𝗂 is more below the elevated areas like mountains. Different surface features like mountains, plateaus, plains and ocean floor are made up of rocks of varying density. Elevated areas are made up of rocks of lower density and low-lying areas are composed of rocks of high density. Heights of different surface features are inversely proportional to their densities. Different relief features are in perfect state of equilibrium, but this state of balance over long geological period is seldom attained. The total weight put by different columns like mountains, plains and plateaus, ocean basins at certain depth below the Earth's surface is not uniform along the line of compensation. The state of isostatic balance is disturbed by the role of denudation and the process of deposition. In mountains and other elevated areas, erosion removes the material and gets deposited in the low-lying areas like coastal plains and ocean floor. Due to the removal or unloading of the crustal material from the mountainous areas gradually becomes lighter due to the loading or deposition, ocean floor becomes heavier. Isostatic balance is regained by the movement of sigma from one column to another column. This is called as isostatic adjustment. Isostatic adjustment or the isostatic equilibrium is restored naturally. It can be said that the concept of isostasy is fundamental to the understanding the dynamic nature of the Earth's surface and to the studies related to major surface features like continents, oceans, ocean basins, mountains, plateaus and plains. It is also useful in the understanding the response of the Earth's crust to the processes like erosion, sedimentation, glaciation, etc. Isostasy is slowly and continuously operating on the Earth's surface.